Hi all, this is Celso Batalha, Evergreen Valley College. This is Astro 10, the Astronomy 10 Introductory Astronomy online course, and I would like to go over the slides of Chapter 1 put out by our publisher. Just initiated here. Okay, so the point of Chapter 1 is to give an overview of astronomy and explain exactly what astronomy is. Astronomy is, as we studied today, is not exactly what people think in general, which is to go in a dark site and look up the sky and then identify constellations and planets and anything that happens to be up there. So astronomy nowadays is the applications of the laws of nature as we learn in physics and chemistry to explain all the process that we can collect information. So as part of this endeavor, astronomers use huge telescopes, which are sort of a bucket collecting light. And light is information about these objects that are so far away that we will not be able, with our current technology, to visit them. So basically, we don't go there, but we collect light that carry information about the processes in which light was produced. And by doing so, we can infer their properties. We can infer how they are, how fast they rotate, how hot they are, and also if they are in the process of um, colliding or not. So chapter 1 also tried to emphasize how vast and how empty empty of stuff we are used to, like the matter that surrounds you right now, made of protons, neutrons, electrons, and light, of course. So if you take light, which is something we know, protons, neutrons, and electrons, something we know. I mean, touch your body and touch the walls around you, touch your computer or your cell phone, and you are touching materials that are made up of these particles. So um, one of the points of this chapter, or maybe the entire course, is to let us know, which will be emphasized towards the end of the course, that this stuff we are used to is not at all the main component of our universe. The main component of our universe, we still don't know what it is. It's called dark matter and dark energy, and these two different aspects of reality, as we know, we are still in the process of figuring out what it is. So, just a small fraction of the visible universe is known, and that's what we are used to, which makes astronomy such an exciting topic that you choose to learn from, and that's how we initiate our journey towards this unknown, if you want to put that way. Um, so how do we take up this journey? Well, because we use science, and science is is a process based on a method, the scientific method. And chapter 1 also emphasized that. So let's go through some basic slides. And so, what's the point of astronomy is to find out where we are in this vast universe. Are we somehow special? Um, our planet is special. Are we in the center of the universe, or is the sun in the center of the universe, or our sun and the planets that orbit the sun that we are used to, and some of them we can see without any sort of a telescopes, are these two objects kind of special in the universe? And the answer to this question, it might disappoint some of you, but probably my open avenues of philosophical thought in some others. And the main point is we are not. I mean, neither the sun or planet Earth is in any way special in the universe, which seems to be so common. And in fact, the universe is populated by stars. There are sun-like stars, stars that resemble the sun, and stars that are, in fact, even less massive than the sun. And planets are not something unique to our solar system. We are going to learn that planets also populate the stars other than the sun, and stars are also not something fixed in the universe. Stars are in transition, if we want to put it that way. Stars are formed out of gas and dust, and gravity takes them into formation, and eventually they go through a process of producing their own energy using fusion reactions in their very core, and eventually they find their end of line, and they die, and in the process of dying they disperse um, atoms recently formed in their interior. These atoms are cast back to sent back to the interstellar medium. So when we think about stars, the stars are kind of a mechanism by which hydrogen and helium, they are very abundant in the universe, are slowly converted into heavier atoms. So when you look at your body, you have carbon, you have iron, you have magnesium, you have calcium. All these atoms were produced inside the stars that no longer exist. So think about scale. So our planet Earth seems to be very big, and in fact it is if we compare ourselves with the size and dimensions of Earth. But Earth is just a planet orbiting the Sun. Sun is just a star that orbits in fact, system of millions, if not billions, of stars that are part of our Milky Way galaxy. Galaxies are complex objects consisting of hundreds of billions of stars, and our Milky Way, our sun, our solar system, and the sun, which is the star in our solar system, is just one that orbits the center part of our Milky Way galaxy, which we are going to learn has a supermassive black hole as, as it is given here. Now, but our galaxy is not the only or the end of the universe. Our galaxy is just one among other few dozens of other galaxies that are part of what we call the local group of galaxies. So local group of galaxies is just a small and poor cluster of galaxies among other clusters of galaxies there is in the universe. And these clusters of galaxies, we will learn, are part of a supercluster of galaxy. And our supercluster of galaxies, the one that our local group of galaxies is part of, the one that our Milky Way galaxy is part of, and the one that our solar system is part on, is called Virgo supercluster. And there are several other superclusters in our universe. And in large scale, that's what we see of our universe is a string of superclusters of galaxies surrounding voids, and these voids happen to be in expansion. So we observe our universe in expansion, and that's why and that's why we perceive, and that's how we account for the universe. The universe is a system that is expanding, is growing in size as we speak, and in large scale, it consists of these superclusters of galaxies, surrounding voids, and superclusters of galaxies, a bunch of little clusters, and we, our local group, is just a poor cluster in which our Milky Way galaxy is one of the members. And the sun is just one star among hundreds of billions of other stars with so many planets we cannot count properly, and that's the universe you are part of. So these slides are available, and and certainly you can review them um, after you're done with this video. So basically, what I do in this video is not to take a lot of time. I would like this videos to be just 15 minutes, 20 minutes, just an introductory aspect of the section, and then you can review the slides if you want, and then you can go to your book and get more information. But one of the aspects that I mentioned previously is light. Light has a finite speed, 300,000 kilometers per second. And this gives some interesting aspects in our endeavor of understanding and attempted to understand what the universe exactly is. Because light has a finite speed, it takes time for light to travel from object to another. I mean, we are used to look around ourselves and think that there is the light that is reflecting off, let's say, the wall around you, takes no time to reach your eyes. So, which means the clock that's marking your time is the same clock that's marking the time of the reflected light on the wall. This is good approximation because we are close to the wall. But if we are talking about, let's say, the distance between Earth and the Sun, the light the Sun sends out to space takes about 8.3 minutes to reach us. Which means if suddenly the Sun disappear and out of nothing just go away, we have to wait for 8.3 minutes to see the effects of that, not only in its gravitational tug, but also in the light itself. If you take about Andromeda, and that's the point of this picture, Andromeda galaxy is about 2.5 million light years away from us, right? Um, so light years is a unit of distance used in astronomy. It's not a unit of time. But it means that light leaving Andromeda will take 2.5 million years, which is a time, to arrive here at Earth. So at 3 million years ago, we were hominids kind of walking in the savannas in Africa or some other Asia place. And, and, and that is when the light that left Andromeda is right now arriving at our telescope. So if you go to the observatory, let's say in September for our public viewing, stargazing, and we are going to show Andromeda to you, you're going to see a little fuzziness through the eyepiece. That fuzziness represents light that left Andromeda when we were initiating our evolutionary process to be what we are 2.5 million years ago. So there are quasars, there are galaxies, there are hundreds of million light years away, which means what we see of them is what they were 100 or so million years ago. So quasars that happen to be 1 billion light years away from us, when you look at them and you get information of these objects, you are in fact getting information of processes that happen not now, but happened at 1 billion years ago. So the farther we look in space, the older, the more ancient aspects of the universe are revealed. And the last part that I would like to mention today is what the scientific method is. The difference between hypothesis, theories, and law, and I think I have a slide here that gives nicely the description. And remember, in our discussions, as we go over through our discussions in this semester, I would like this to be emphasized. Exactly what science is. I mean, science does not deal with truth. So usually in the religious setting, the word truth is very much emphasized. Not so much in science. It doesn't mean that we don't strive to It doesn't mean that we lie. That's not the point. It doesn't mean that we hide information in order to publicize some agenda or something like that, like a conspiracy theorists would perhaps indicate. Science is a method by which we try to explain how things behave. I mean, how nature works, basically. And all the explanations we have are based on the amount of data, the wealth of data that has been accumulated up to the point that our explanations came by. And they are pretty much consistent. You cannot take science done in the United States and say, okay, the science done in China is different. No, it's the same. It's a universal language because it's a universal process. So, how does this process come by? It initiated and ended in nature. So what do I mean by scientific method is initiated in nature and ends in nature? Here it is. You must observe something that goes on. So you observe processes or you observe some pattern, some repeatable aspects of nature, like the sun rise in the east and set in the west. Next day, the sun is again rising in the east and set in the west. And this repeats on and on and on through the years. And then we realize, well, there is some pattern here. So when this pattern repeats, the mind creates some explanation. Why is this happening? So the universe is not chaotic. It's not something that cannot be explained. And perhaps this is the most beautiful and fascinating aspect of science, is that you can explain things. So, and then you come up with an explanation. So that explanation is called hypothesis. It's an idea. Sometimes can be very stupid, very kind of a preliminary, but it's just an idea. But when you present a hypothesis, this hypothesis in the realm of science must be supported by some sort of basic and logic. It cannot be out of logic. And your hypothesis must be testable. So, which means I cannot say that the sun is rising in the east because there is a sun god called Apollo that is taking the sun in a trip across the sky. I cannot say that. I cannot use that according to science nowadays as a valid hypothesis because I cannot test. I cannot summon Apollo, God Apollo, to my laboratory and figure out what it is. Every single element in a hypothesis must be able to be tested so that the aspect of science as being reproduced in any other part of the globe, if you're not universe, can be a real thing. So aspects of your hypothesis must be testable and must be verified, and it should be logically sound. It cannot be kind of a crazy, if you know what I mean. So the hypothesis that you create um, must be able to suggest a prediction. So the sun is rising in the east, but you observe that every single day the sun is rising in the east, but is moving a little bit more towards the south. So every day it rises southeast to the point that eventually it start. When I say eventually, is when it reaches winter solstice, it starts rising a little bit more to the north. So we have this pattern going on throughout the year, and then you create hypotheses to explain how that work. You can, for instance, think that we are in the center of the universe and the sun just orbit Earth, or you can create a model or hypothesis in which the sun is the center of the universe and Earth goes around, as it was done a couple of thousand years ago. So hypotheses become sometimes so subject to tests, they might even become a theory. So a theory is when hypotheses have withstand a lot of tests, and then you have all um, mighty, if you will, theory. Now, theories, as I said, they are not truth. They are not ultimate truth. They are not point of belief. Theories are there because they can explain what the amount of data we have up to a certain point. And I will give an example. Newton's gravitational theory, developed in the 1700s, was well strong up to late 1800, when Einstein came with his general relativity theory, and was able to show the theory was not right. And it could be applicable to certain range in velocity, but not when velocity, when bodies were moving at very high speeds closer to the speed of light, and then a new theory should be then employed. So so theories are good to explain data, and if their predictions are not met with observations, then they must be either refined, or they have to cast it aside because they are not good. So again, that's why I said science starts with nature and ends with nature. Nature has the last word. The theory is not more important than nature. In some religions, this might not be it. Their belief sometimes is more important than evidence, and then you put aside the evidence in order to support a belief system. In science is different. What we observe, what we measure, what we consistently use to explain how nature behaves has the last word. And if my theory, what I think is the right way of nature behave, does not match with observations, kiss goodbye to your convictions. And pretty much that's how science goes. So with these remarks, I would like to just end this video, and hope to see you in the chat room.